Welcome to the video corresponding to Chapter 4, Section 4.7 of Basic Sentential Logic and Informal Fallacies, text used for Philosophy 10 Introduction to Logic at UC San Diego. The topic for this section is tautologies, and in particular using the proof method to demonstrate that a statement is a tautology. Now, what we've done so far is we've introduced inference rules, replacement rules. We have conditional proof, indirect proof. So we've got all of our proof tools. Now we're going to use these tools in a different sort of way. Now, the proof method is a method for demonstrating validity, argument validity. In other words, demonstrating that if a given set of statements, the premises of an argument, if that set is true, then another statement, the conclusion, is true, has to be true. Given that this is the case, is there any way we can use the proof method to show that a statement is a tautology, which is a different kind of question, right? Determining whether a statement is a tautology or not. We did that with truth tables in Chapter 2. Remember, you would do a truth table for the statement. And if the statement's truth column was only T's, then that statement would be a tautology. Is there any way we can use the proof method to do that work for us? The answer is yes. And here's the reasoning. If we can derive a statement from no premises, right? So we take that statement, we treat it like the conclusion of an argument, right? The statement we're trying to determine if it's a tautology or not. We treat that like the conclusion of an argument, but we don't have any premises, okay? If we can derive that statement with no premises, then we know that that statement will follow from anything, okay? If you can derive it from no premises, you can derive it from any set of premises, right? If I just give you, you derive it from no premises, and then I say, well, here's 5 premises, derive it. You just do exactly the same steps you did before. Okay, so you'll still be able to derive it even if I give you any set of premises, if you can do it from none. Well, what that means is that any argument that has the statement in question as its conclusion is going to be valid. Doesn't matter what the premises are. If that statement is the conclusion, that argument will be valid. Why? Because you'll be able to derive that statement. And deriving the statement is what constitutes argument validity. It doesn't constitute it, but it indicates argument validity. The only category of statement for which that's true is a tautology. Okay? An argument with a tautology for its conclusion is going to be valid no matter what the premises are. That's not necessarily true for a contradiction or a contingency. So that's how we can use the proof method to determine argument validity. If we can derive that statement from no premises, then that demonstrates that that statement is a tautology. So here's how it works in practice. You'll be given an argument like this. Now, this is just like the arguments we've been doing all along in Chapter 3 and 4. The only difference is that there's no premises here. All we have is the conclusion. We've got the slash, we've got the triple dot, and we've got the conclusion statement, just like in all of the examples we've done so far. There's just no premises. Now the goal is to do what we've always been doing. We're just going to try to derive the conclusion. The difference is no premises. How can we do that? Well, we're not going to be able to start off by using any rules, because replacement rules and inference rules all apply to lines that we already have in a proof. We don't have any lines in the proof yet, because we're starting with nothing. We're starting with no premises. By the way, let me just be clear on something. This is the conclusion. This is not a line in the proof. Okay? This is just telling us what we're trying to derive. We don't have any accessible lines yet. So we're going to have to start with either a conditional proof or indirect proof, because that's the only way we can get going if we don't already have some lines available. Well, what we're trying to derive here is a conditional, so I'm going to use conditional proof. Now, I could use indirect proof. I could, for instance, one approach would be to assume the negation of this entire thing and derive a contradiction. And you'd be able to do that. I can also use conditional proof. Assume this antecedent, derive this consequent. That's what I'm going to do. So I'm going to assume the antecedent, if P then not P, and that's my assumption for conditional proof. That's the antecedent of the conditional I want to end up with. Consequent is not P. So now my goal is just to derive not P. And you can see that's going to be pretty easy. I can do conditional exchange, P or not P, duplication to get not P. And there it is. Boom. It only took 3 lines. Now I can close this subproof off. Next line can only be a conditional whose antecedent is the ACP, whose consequent is the last line. If P then not P, then not P, which is the conclusion. So I'm done. I've managed to derive this statement starting with nothing, starting with 0 premises. And so I've shown that this statement is a tautology. Let's do another example, because it turns out if we flip these, it's also a tautology. If not P, then if P, then not P. So I'm just going to flip it around. This statement is also a tautology. I'm also going to use conditional proof. I'm going to assume the antecedent and derive the consequent. So I'm going to assume not P. My goal now is to derive this, and it's pretty easy. I can get not P or not P by duplication. I could also, another way I could justify that would be 1 DI. That's another rule that could take me from this to this. Either of those 2 justifications would work. Now I'm going to do conditional exchange on this. Wedge becomes a horseshoe, negate the first component. So I get if P, then not P. That's the consequent I want. So now I'm going to close the conditional proof. And next line, conditional, ACP is the antecedent, last line is the consequent. And that is the statement I was trying to derive. So I've demonstrated that that statement is a tautology. Okay, let's do one more example, one that's a little more involved. Now, if you look at this, this is a tautology. And in fact, if you look at this tautology, you should be able to see something. This tautology is basically embodying the rule of hypothetical syllogism. If I have P and Q and I have, if I have if P then Q and I have if Q then R, then I can get if P then R. That matches that. Okay, so by hypothetical syllogism, I can get that. Let me point something out here. If you want practice doing tautologies, then one source of tautologies is you just take any inference rule and you make a conditional whose antecedent is just the conjunction of all of the lines up on the top above the line of the inference rule, and whose consequent is the line, is the statement below the line. Right? So if we were to write out the rule for hypothetical syllogism, we would have if P then Q on one line, if Q then R on another line, therefore you can derive if P then R. So conjoin everything above for the antecedent, and then the consequent, just use the thing below the line. And that's going to be a tautology. And then you can derive that tautology. You can use that for practice. Now, if you use the rule itself, it's going to be a pretty easy proof, right? So if I used hypothetical syllogism to derive this, it would be easy, because I could use conditional proof, and I'm going to use, I could assume this, goal is to derive that. Well, once I've got this assumed, I just disjoin all of these, and then I use the rule of hypothetical syllogism to get that. It'd be super easy. So in order to make it more challenging, I'm going to do this without using hypothetical syllogism. Okay? And in fact, I'm going to do this in a really weird way. Okay? Why? Part of it is just to sort of give you, sort of expose you to a sort of proof that's done in a kind of counterintuitive way. Secondly, is a sort of demonstration of something that I've said a number of times in class, which is that there's an infinite number of ways to correctly do any proof. So I'm going to do this proof now in a way that you probably would not do if you tried this proof. You could probably do this proof 10 times, 10 different ways, and never come up with the way I'm going to do it. But that's okay. There's an infinite number of correct ways. The 10 ways you did it could all be correct. That's fine. Here's another way to do it. I'm going to assume Q, and you'll see why in just a second, because I want to derive the conditional if Q then Q. Why do I want if Q then Q? You'll see. Assume Q, get Q and Q by duplication on 1, simplify the first conjunct, Q off and close my subproof, and then I get if Q then Q, and that's by 1 through 3 conditional proof. Now, by the way, you can use this little technique right here at any point in any proof to derive a conditional whose antecedent and consequent are the same statement. Right? So if at some point you're doing a proof and you want if R then R, you can just use this technique right here to get it. Okay? Well, now what am I going to do? Well, now I'm going to do a conditional proof. I'm going to assume this antecedent, and my goal is going to be to derive that consequent. So I'm going to assume that. And my goal is to derive if P then R. Now, as I already mentioned, if I simplify both of these off, simplify P then Q, simplify Q then R, I could do hypothetical syllogism right now to get if P then R. Then I close this subproof off and I've derived this. And that's easy. That's too easy. Okay? So if you're giving yourself more practice by turning inference rules into tautologies, make it difficult by not using that same inference rule in the proof. Okay? So I'm going to do that. I'm not going to use hypothetical syllogism. Well, what can I do? Well, here's what I can do. I can do contraposition on 6. So if P then Q becomes if not Q then not P. Now I'm going to do conditional exchange on 4. Oops, that should be 4. Sorry about that. Okay. So horseshoe became a wedge, Q became not Q. Now, notice here, this is the disjunction of those two antecedents. So I can do dilemma on, actually it's not 489, it is 789. Is that right? Yes, I have two conditionals, disjunction of their antecedents, get the disjunction of their consequence, P or R, and that's by 789. Dilemma, and this was conditional exchange on line 4. Sorry about that. Okay, now notice this is just a conditional exchange away from the conditional I wanted. So I do conditional exchange on line 10 to get that. Okay, let me just correct these again really fast here. That's 4 and that's 7. Okay. Well, now I've derived the consequent I want. I assumed this right here, and I managed to derive that consequent, if P then R. So now I can close this subproof off, and let me correct my lines here again. That's 4, and that's 7. Okay. 5 through 11 conditional proof, and that's this conditional. I did not use the rule of hypothetical syllogism, but I did use this. Okay, I needed, at least the way I did the proof, I needed to get this disjunction, if Q then not Q, this tautology. How did I get it? Well, I first derived if Q then Q and did conditional exchange on that line. So that gave me a component I needed in order to derive that statement. Like I said, you could probably do this proof 10 or 50 times and never do it exactly this way, but that's okay. Infinite number of ways to correctly do any proof. So this demonstrates that that statement up there at the top is a tautology. Okay, what about this example? One premise, which is F, conclusion, either if G then H, or if not G then J. Now what's interesting about this is if you look, the premise is just an atomic statement, F, and that atomic statement doesn't show up anywhere in the conclusion, which is kind of weird. One thing that could mean is that the conclusion is a tautology. You'll be able to derive that conclusion without even having to use that premise, because you could derive it from 0 premises. So I could also derive it from that premise. I just go through the same set of statements. I'm just never going to cite line 1. That's okay. I can do that. Well, how am I going to do it? Well, notice, remember, one way to derive a disjunction is to use conditional proof. You derive the conditional that this would be if you use conditional exchange. Then you use conditional exchange to get the disjunction. Okay, so for example, I'm going to assume this, the negation of that. Why is it the negation? Well, if you know what I'm doing, if you followed my strategy, you know why it's the negation. If you didn't follow it, wait until I'm finished with this proof and then you'll see why I assumed the negation here. Okay. Well, I've assumed this. My goal now is going to be to derive if not G then J, because I want the conditional with this antecedent and that consequent. Okay? How am I going to do that? Well, do conditional exchange on 2, horseshoe becomes a wedge, negate the G, G becomes not G, everything else stays the same. I'm going to do De Morgan's on this to get G and not H. I'm going to simplify the G off. Why? Because what I want to do is I want to get a piece here that I can use to eventually get this conditional. And if I get G by itself, I can disjoin. I can use DI to get either G or J, do conditional exchange. If not G, then J. Now I've got this. Okay. So I managed to derive the consequent of the conditional I want. So I can, now's a good time for me to end this subproof. Boom, boom, boom. Next line can only be a conditional that has this antecedent and that consequent. Okay, now notice, the proof is not over. Okay, so some of you guys get this, which is fine. If you get it, you know, don't worry about what I'm about to say. But some people don't see this right away. So I want to talk through. Some people might say, well, look, hey, Rick, it's conditional proof. Why aren't you assuming this? Why are you assuming the negation? Well, this isn't a conditional. Okay, so I'm not using conditional proof to derive this statement here. That's not a conditional. I can't use conditional proof to get this statement. So if I were to assume this and derive that, what I would get is if this, horseshoe that, which does not help me because this isn't a horseshoe. I want a disjunction here. Okay, I want this to be a disjunct and this to be a disjunct. Okay, but I know that if I get this conditional, then watch, when I do conditional exchange on this, all of a sudden now I do have this disjunction. Okay? But in order to get this disjunction, I had to have the conditional where this was negated, right? Because when I turn the horseshoe into a wedge, I have to negate the first component. So this comes off. So if this is the disjunction I want, which it is, that means this is the conditional I want. Wedge becomes a horseshoe, but look, I have to negate that. Okay, that's why This negated thing was what I assumed here. This is the antecedent of the conditional I want. This is the conditional I want, okay, with a negated antecedent here. Why do I want this conditional? Because this is what I can turn into that in one step, and that's the conclusion. Okay. Let's do the same proof, but do it a different way. Same proof, same conclusion. Conclusion is still a tautology. I'm going to do my little trick here to get if G, then G. So assume G, G and G by duplication, go back to G by simplification, 2 through 4 conditional proof. That's just one little technique that you can bust out to get a statement, a conditional that has the same statement as antecedent and consequent. And it's useful sometimes to have these, to have those, and you'll see why. From this, I will be able to derive this without using indirect or conditional proof. I'll just be able to manipulate this with inference and replacement rules to get that. Okay, so that's how I'm going to do this proof this time. How am I going to do this? First, I'm going to turn this into a disjunction, not G or G. Now, I'm going to use DI to disjoin this, okay, H or J. Remember, with DI, it says if you have a statement, you can disjoin any other statement to that. Well, I've got this, and I can disjoin any statement I want. Well, I'm going to disjoin this disjunction. That's fine. Why am I doing it? Well, because now if you look, in this compound statement, I've got 2 G's, an H, and a J, which is what I'm eventually going to want up here. 2 G's, an H, and a J. And in fact, one of the G's is even negated, right? Now, not every time you look at a proof can you just count the number of statements and guarantee that you'll be able to manipulate that into that. But in this case, you will be able to. What I'm going to be doing is using association and commutation and such to turn this into that. Okay, and here's how I'm going to do it. First, I'm going to associate. So right now, I have 3 disjuncts. Let's go back here. You might look at this, you might say, well, look, it's actually 4 disjuncts. Well, it is, but I can conceive of that as statement or statement or statement. So I can kind of ignore the fact that this is itself a disjunction for now. And I can sort of see this as 3 disjuncts, here, here, and here. And right now the first 2 of these are associated, but I'm going to use association instead to move the parentheses over and associate these 2, this and that. Okay? So I've associated the first 2 and left the last one out by itself this time. Okay, next, okay, I'm going to use association again just for this middle part. So let's go back up here. Let's look just at this middle part, or just this chunk. It's 3 disjuncts, not G, G, and H. I'm going to move these parentheses to the right and associate the G with the H. Boom. Okay. Now, I'm going to commute. I'm going to just take this disjunction and flip the order of disjuncts. I'm going to move the H to the left, G to the right. Everything else stays the same. Okay, so now I've got things in the right order. I've got a G, an H, a G, and a J. G, H, G, J. Now what I'm going to do is associate them correctly and then turn everything back into a conditional and hope that it works out. Hope that I get the right negations in the right place, and it will work out. Okay, so now that I've done the commutation, I'm going to move these parentheses back over to the left So looking at this part, it's 3 disjuncts. The last 2 were associated. Now I'm going to associate the first 2. I'm just going to move these parentheses over to the first 2 here. Now I'm going to, notice I'm going to conceive of this again as 3 disjuncts: statement, or statement, or statement. Right now, these 2 are associated. I'm going to instead associate these 2, the G and the J. Now, the disjunction is right. So this is a disjunction, but each disjunct is supposed to be a conditional. Right now, each disjunct is itself a disjunction. So I'm going to do conditional exchange. First, I'm going to do conditional exchange on the second one. Wedge becomes horseshoe, negate the first component, and sure enough, not G then J. That's exactly what I wanted. Now I'm going to do conditional exchange on the first disjunct here. Wedge becomes horseshoe, negate first component, if G then H. And sure enough, that's what I wanted, if G then H. And I'm done. I've derived this statement technically from F because I was given F as a premise, but I never used F. So I would also have been able to do exactly this sequence of steps if this were a tautology type proof where I wasn't given any premises at all to begin with. Okay, that's it for this video.